Welcome to Suchithra statistics classes. Today we are going to discuss about law of large numbers. Law of large numbers is a name given to a series of theorems for a broad class of linear functions y equal to phi of x1, x2, etc. xn. The standard deviation of y tends to 0 as the number of variables n increases without limit. That is, standard deviation of y, sigma y tends to 0 as n tends to infinity. The simplest case of this is when xi's are all independent. That is, standard deviation of xi equal to sigma, that for all I varies from 1 to n, and y equal to x bar. There are two series of law of large numbers that deals with the limiting behavior of random sequence. Weak law of large numbers deals with random sequence which converge in probability. Strong law of large numbers deals with random sequence which possess almost sure convergence, that is, convergence in distribution. Now let us think about what is convergence in distribution and convergence in probability. Xn tends to x in distribution, denoted like this. If fnx tends to fx for all continuity points of x of f. Here fn, that is fnx, is the distribution function of xn, and f, that is fx, is the distribution function of x. And fnx equal to p of xn less than or equal to x, and fn is equal to p of x less than or equal to small x. Xn tends to x in probability, denoted as xn tends to x, here p, means that for every epsilon greater than 0, we have probability of mod xn minus x greater than epsilon tends to 0 as n tends to infinity. That is, as n tends to infinity, the difference between xn and x becomes so small, which we can imagine as small as possible, that is epsilon. Now let us discuss Bernoulli law of large numbers. We are very well familiar with Bernoulli experiment. Bernoulli experiment is random experiment with only two possible outcomes, say success and failure. If you are only performing one trial, that becomes Bernoulli distribution, and if you are performing n trials together, that turns to binomial distribution. Now, let us read what Bernoulli law of large numbers says. Consider a random experiment with only two possible outcomes, say success and failure. Let P be the probability of success remains unchanged from trial to trial. Let n independent trials of the experiments being considered. Let xn be the number of successes in these n trials. Bernoulli law of large numbers says that for any epsilon greater than 0, p of mod xn by n minus p less than epsilon tends to 1 as n tends to infinity. That is, in Bernoulli law of large numbers, the statement is p of mod xn by n minus p less than epsilon tends to 1 as n tends to infinity, where P is the probability of success. Xn is the number of successes out of n trials. And epsilon is the smallest positive number which we can imagine. Now let us prove this Bernoulli law of large numbers. By using Chebyshev's inequality, we are proving this Bernoulli law of large numbers. Here, this is the statement which we want to prove. So, we are going to adopt the Chebyshev's inequality, which is similar to the expression probability of mod xn by n minus p less than epsilon. By Chebyshev's inequality, we know that p of mod x minus mu less than or equal to t sigma greater than or equal to 1 minus 1 by t square. Again, by Chebyshev's inequality, we know that we have to find mean mu and standard deviation sigma of random variable x. Here the random variable is xn by n. So we have to calculate mean of xn by n and variance of xn by n. And again we know that xn is a binomial random variable. Mean of xn by n, that is expectation of xn by n, is equal to 1 by n expectation of xn, that is np. Since xn follows a binomial pattern, divide by n, that is p. Variance of xn by n is equal to 1 by n square variance of xn, that is npq divided by n square, that is pq by n. Therefore, standard deviation of xn by n is root of pq by n. So, by applying Chebyshev's inequality to this statement, we can rewrite this as p of mod xn by n minus p less than or equal to t into, instead of sigma, root pq by n greater than or equal to 1 minus 1 by t square. Comparing this expression and this expression, we can write epsilon equal to t into root pq by n. Put t into root of pq by n is equal to epsilon. Then t equal to epsilon into root of n by pq, t square equal to epsilon square into n by pq, 1 by t square equal to pq by n epsilon square. We know that p lies between 0 and 1 and q equal to 1 minus p. Therefore, the maximum value of p into q is 1 by 4. That is, pq is always less than or equal to 1 by 4. Therefore, p of mod xn by n minus p less than epsilon is greater than or equal to 1 minus 1 by 4n epsilon square. That is, when we are substituting 1 by 4 instead of pq, there won't be any change in this inequality because 1 by 4 is maximum of pq. And 1 by 4 n epsilon square tends to 0 as n tends to infinity. Therefore, p of mod xn by n minus p less than epsilon tends to 1 as n tends to infinity. Or we can say p of mod xn by n minus p greater than epsilon tends to 0 as n tends to infinity. This is the proof of Bernoulli law of large numbers. Now let us think about necessary and sufficient condition for a sequence xn of random variables follow the weak law of large numbers. That is, let Bn equal to variance of x1 plus x2 etc. plus xn. Then limit n tends to infinity, Bn by n square is equal to 0. This is the condition for satisfying weak law of large numbers or following weak law of large number for a sequence of random variable xn. So let us read the statement. If x1, x2, etc., xn are independent and identically distributed random variables with E of xi equal to mu and variance of xi equal to sigma square exists for all I varies from 1 to n, then necessary and sufficient condition for the sequence xn of a random variable to follow the weak law of large numbers WLLN is that limit n tends to infinity, Bn by n square equal to 0, where Bn equal to variance of x1 plus x2 plus etc. xn. So for showing whether the sequence of random variables hold weak law of large numbers, first calculate Bn and calculate Bn by n square. If there exists any n in the denominator, as n tends to infinity, Bn by n square tends to 0. Then we can conclude whether it satisfy this weak law of large number or follow weak law of large numbers. Thank you. Thank you for watching.